On the right, you can see a simulation of a few photons that just grazes around a Schwarzchild black hole. And on the left, this is a real observation of what appears as a photon ring. Stars greater than 20 times the mass of our sun collapses into black holes, undergoing a violent supernova explosion, leaving behind a dense core from which even light cannot escape. Although you cannot directly see astrophysical black holes, you can study them based on how they affect their surrounding. Albert Einstein in the year 1915 gave us the general theory of relativity, which changed the whole understanding of space and time forever. He gave us a much more comprehensive theory of gravity, and one of its main implications being how a mass can warp the space-time around it. The Einstein field equation famously relates the geometry of space-time to the distribution of matter within it, given by this equation. Although this is a much complex equation with tensor notation, the first ever solution to this equation was actually given by the Schwarzschild metric. In the year 1916, just after a year, Carl Schwarzschild gave us the first ever solution to Einstein's field equation. This solution was a black hole which was time independent, spherically symmetric, and static. Schwarzschild metric has a time part and a space part associated with it. The ds term here is an invariant quantity, and ds squared in Euclidean space is just the hypotenuse of the line joining the dx and the dt axis. So you might be wondering that why am I going through all of this? Well, in this video, I will give you the broader implications of what a photon ring or a photon sphere actually is around a black hole. And in order to do that, I will lay down a mathematical framework using general relativity in order to find what is the closest path that a photon can travel around a black hole before it either plunges into the black hole or gets lost into space forever. So in order to do that, we need to understand what the Schwarzschild metric and the Schwarzschild spacetime is. And then from there we can simplify our way to find the answer to this question. What is that special orbit where a photon of light just has enough energy to orbit around a black hole? This photon ring or photon sphere has a huge implication in the field of astrophysics and cosmology in general, because by observing these photon spheres directly, we can get a direct observation of what is going on very close to the event horizon of the black hole, which has never been done before. The two current images of the black hole that we have taken by the Event Horizon Telescope gives us an overall broad picture of the emission ring around the black hole. The photon ring is embedded in there somewhere, but we currently do not have the resolving power to actually disentangle the photon ring from the actual picture of the black hole. In order to do that, we need higher resolution, and my further upcoming videos will dive deep into that. But here, let's try to actually derive what that stable path is. Without going into too much details, first we actually write down the Schwarzschild metric, then we write down the forward velocity in the equatorial plane, then we define two Killing vectors, which are time and rotational symmetry dependent. Then we define two quantities, E, which is the energy per unit mass, and L, which is the momentum per unit mass. The forward velocity in relativity is a four-dimensional vector that combines an object's velocity in space and its rate of proper time tau, as shown here, where u of 0 is the time index, u of 1, 2, and 3 are basically the spatial indices of that vector. Proceeding further with our calculation, first we set the term ds squared to 0, then we set dr to 0 because we are in the equatorial plane, then we simplify subbing in for the special E and the L term that we defined. Finally, we get the effective potential. Then we do a derivative of the effective potential with respect to r, and then set that to 0 in order to get the orbit or the energy required at r equals to 3 gm to completely take an orbit around the black hole. Plotting that effective potential as a function of r, we clearly see that at r equals to 3 gm, there exists an unstable orbit. It's unstable because a little nudge from that orbit can either send the photon into the black hole or outside into space to infinity. Now switching gears in terms of real data. This was the first observation of M87 star using the Very Long Baseline Array in 1999. Zooming in and increasing our resolution with the GMV observation, we can see much more details. Finally, this was the famous image of the M87 by the Event Horizon Telescope, where we can actually see the emission ring around the black hole. Now, for the very first time ever, Broderick and collaborators have been able to disentangle the photon ring from the overall picture of the black hole. Using sophisticated ray tracing simulations, we can see that the photon ring at n equals to 0 is the innermost and the brightest ring. It represents the photon that makes a single, nearly complete orbit around the black hole before escaping. The photon ring at n equals to 1 consists of photon that makes one complete orbit around the black hole before escaping. This ring appears much dimmer because it is less likely to observe due to the lower probability of photons doing a full orbit. Similarly, the n equals to 2 involves photon completing 2 full orbits. This is even less dimmer because the probability is even less. The gravity is so strong that a little nudge, as we showed, is enough to throw off that photon. So 2 orbits is much less probable. So I hope this video was somewhat useful and you got something to take away from here. Well, the idea of this video was to lay down the mathematical groundwork needed to actually further discuss about photon rings and its direct observations. As you can see, the future of imaging black holes is actually going to be much brighter. And with the next generation of Event Horizon Telescope coming up and further development in space and balloon VLBI, we will be able to resolve the photon rings. As I already mentioned, these photon rings will help us uncover the mysteries of the black hole in a direct observational way. Who knows in the future if we can actually understand the true nature of quantum gravity observing these photon rings. I definitely look forward to the future, and I hope some of you are too. This video was made possible with the use of MANIM. MANIM stands for Mathematical Animation Engine, and MANIM has been developed by Grant Sanderson, whom you might know as 3 Blue 1 Brown. This mathematical engine was written in Python, and I used that tool to make this video possible. So a huge thanks to the MANIM community in developing this wonderful tool that helps creators like us make nice videos out of. With that, I'll end this video here, and in the next few videos, I'll actually delve deep into direct observations of such photon rings. Also, a special video is coming up where I got the opportunity to visit the Very Large Array Telescope in New Mexico and got to climb in one of its dishes, got to see the guts of the receiver. So that video is also coming up. Stay tuned. Catch you guys in the next one really soon.